Okay, hello everyone. I'm Haran Ma. I'm now a third-year PhD student at UCLA. Today I'm going to present our paper, Mako, a low-pulse high-throughput evacuating collector for memory-disaggregated data centers. This is a joint work of UCLA, Ohio State University, and Australian National University. Nowadays, the data center has the problem of memory capacity bottleneck. The growing of DRAM memory capacity is slower than that of processor computation. And the memory in data centers is often underutilized, causing a big resource waste. So cloud providers are now thinking how to solve these problems. One of the most promising directions is to do memory disaggregation. Well, what is memory disaggregation? As we know, conventional data centers are built with monolithic servers. But memory disaggregated data centers contain servers dedicated to individual resource types. CPU servers are usually equipped with very strong cores and some amount of memory, while memory servers have a huge amount of memory but only has weak compute power. They are connected through special high-speed network stack such as RDMA over InfiniBand. Memory disaggregation can improve resource utilization and has better elasticity. On disaggregated memory, one process can run on one CPU server and multiple memory servers. The process does the computation on the CPU server, and when it uses more memory than the local memory capacity, it will swap out data to memory servers. More specifically, for managed applications written in Java, the CPU server runs a Java virtual machine with a heap that is logically split into a number of partitions. Each partition is backed up by physical memory on a memory server. The small amount of memory on the CPU server serves as a software-managed inclusive cache. The remote data access granularity is at the page level, and accessing data on remote servers is only about 10 microseconds, which is a lot faster than accessing disks, but still a lot slower than accessing data residing in local memory. So if the application running on memory disaggregation does not have good locality, then this latency difference might cause big performance problem. Unfortunately, many managed applications written in Java using Concurrent GC fall into this category. Currently, a lot of modern Java applications have very big heaps and needs to meet millisecond levels quality of service. Meeting this level of service agreement requires a garbage collection algorithm which can compact the heap while Java threads are running. So new concurrent collectors like Shenandoah and ZGC are proposed. They only have very short stop-the-world phases and do the marking and evacuation concurrently with the application threads. However, when running on disaggregated memory, this kind of GC encounters very big performance problem. We run traceable benchmark with Shenandoah GC under different local memory ratios. Though their pause time are still in millisecond level, the application throughput decreases sharply when the local memory becomes smaller. And for some other applications, the slowdown can even reach up to 25 times. But why? Why Concurrent GC slows down the application so much? There are two main reasons. First, GC is a typical graph traversal workload which has barely no time and spatial locality. Second, the application threads and the GC threads are executed concurrently, and there is no correlation between them. The application and GC will compete for local memory and RDMA bandwidth. Now that we know the reasons, is there any way to improve the performance? Here, we have a very straightforward idea, which is to just offload garbage collection to memory servers. Because after doing this, we can reduce resource contention and the interference between application and GC. And most data is on memory servers, so GC is also near data, which means higher throughput. However, can we easily achieve that? The answer is no. There is a big challenge in doing this. The challenge is there is no efficient way to enforce memory coherence between the CPU and the memory servers. In other words, if memory servers modify some contents in memory, the CPU server cannot immediately know that. And clearly, GC threads offloaded to memory servers need to write memory. So simply offloading GC to memory servers without careful synchronization would cause big correctness problem. Now that we know the reasons, is there any way to improve the performance? The answer is no. There is a big challenge in doing this. The challenge is there is no efficient way to enforce memory coherence between the CPU and the memory servers. In other words, if memory servers modify some contents in memory, the CPU server cannot immediately know that. And clearly, GC threads offloaded to memory servers need to write memory. So simply offloading GC to memory servers without careful synchronization would cause big correctness problem. There are two phases that GC threads need to write memory. First, the concurrent updating reference phase. In this phase, the GC threads need to update the old references to point to the new addresses of evacuated objects. However, this update is invisible to the CPU server. If the object containing the reference is now also on the CPU server and is swapped out later, then this swap out operation will override the updated reference on memory servers. Second, the concurrent evacuation phase. During this phase, most modern garbage collectors usually install a forwarding pointer in the object header if they move an object. And similarly, if the page containing that object is also on the CPU server, then after the CPU server swaps out that page, this pointer would be lost on memory servers. We will later show specific examples for these two phases. Here, I want to introduce our key design idea first. So to solve the problem in these two phases, we propose this heap indirection table structure. We call it HIT. The HIT is inspired by the object table design, which was used in Smalltalk and in the early days of hotspot Java virtual machine. But our HIT is a distributed data structure designed for our distributed region-based GC. It manages regions spanning multiple memory servers. The HIT is a collection of tablets. Each tablet corresponds to a heap region. Each entry in the tablet stores the actual address of an object in the region, and each reference type object field in the heap contains an HIT entry address instead of the actual object address. Techniques centering around this HIT structure can solve the problem we just showed. Our work is the first one that brings the HIT design into the memory disaggregation setting. Let me now use two examples to show why simply offloading GC does not work in those two phases and how our technique solves it. As we just said, the first phase in which memory servers write memory is the concurrent updating reference phase. Assume now we are in that phase, object A is on a memory server, and it has a field pointing to the stale object B. This field needs to be updated to the new address of object B. But before the GC threads on memory servers update object A's fields, the CPU server may want to access object A, so it will swap in object A. After data swap in, the CPU server mutates some fields of object A to 0. At the same time, the GC threads on memory servers are also working and updated object A's field to point to the new address of object B. Until now, everything is fine. But after a certain amount of time, the local memory on the CPU server would be full. Then it needs to swap out some data. And it would be possible for the kernel in the CPU server to choose to swap out the page containing object A. Then we can see the updated field of object A is overwritten to the old value. And this clearly causes correctness problem. But after we have the heap indirection table, it eliminates the need to directly update pointers at both the CPU server and memory servers, which means the previous problem in concurrent updating reference phase is eliminated. It's the nature of our HIT. Let's take a look at this example. First, the GC threads copy object B on the memory server to the to space. After that, the GC threads update the HIT entry to let it point to the new address of object B. We can see we only need to update the HIT in the evacuation phase rather than update every reference field pointing to object B in the updating phase. So no concurrent reference updating phase after we have the HIT, and clearly the problem in that phase does not exist. The second phase is the concurrent evacuation phase. Take this case as an example. There are 4 objects in region 0. 3 are alive and 1 is dead. Object B and C is on the same page. The application on the CPU server would like to mutate object B's field. Then it needs to first swap in the page containing object B. Object C is also swapped in because the swap in and swap out is on the page level. Now, the application threads want to access object B. In most concurrent GC such as Shenandoah, the mutated threads would move it to the to space first. So object B is moved, and then the application threads are allowed to mutate object B. At the same time, the GC threads on memory servers are doing work and evacuate all alive objects in region 0. Similar to previous example, after a certain amount of time, the local memory on the CPU server would be full. Then it needs to swap out the page containing object B. After writing back, we can see the installed forwarding pointer in object C's header is lost. But this information is needed to update the references pointing to object C. So this error can actually crash the whole system. Then how do we solve this problem using the HIT? Actually, this problem is caused by the granularity mismatch of object access and data swapping. JVM accesses data at object level, while the operating system kernel manages data at page level. But if we synchronize on each object access, then that would incur too much overhead. So we designed a tablet lock so that we can achieve the region level synchronization. When the memory server is evacuating a region, the corresponding tablet will be locked. Access to that region on the CPU server are then also blocked. After the evacuation is done, the lock will be released, then the access can continue. As for objects accessed before its region is evacuated, they are directly moved by mutators on the CPU server and will not be blocked. Let's take a look at an example. Same here. Concurrent evacuation has started. The CPU server wants to access object B, so swapping object B. A small difference here is that the corresponding tablet entries are also swapped in. And we move object B to the to space before accessing it. Then mutate it. Suppose now the GC threads on the memory server prepare to evacuate region 0. Here is a small difference. The tablet entries of region 0 need to be written back to avoid evacuating the same object twice. After writing back, okay, here is the key operation. Region 0's tablet is locked. From now on, the mutator on the CPU server cannot access objects in region 0 and the corresponding tablet, while we can still access object B because it has already been moved. Until the evacuation for region 0 is finished, the lock is released, and the application threads on the CPU server blocked on region 0 can continue. And swapping out object B to memory servers will not cause any problems now. You might want to ask, why can't we just add a lock to the region when it is being evacuated? Why do we need the HIT? Two reasons here. First, HIT simplifies the lock design, because accessing each object requires the access to the tablet. If we can lock the tablet, then our access to that region is blocked. Second, the reason why swapping out the stale object B and C would not cause any problem is because they are not modified on memory servers. Since we already have the indirection table, GC threads now do not need to modify the forwarding pointer in the object header. So as you can see, the problem in concurrent evacuation phase is also solved. Okay, it comes to the last part. For evaluation, we run Mako on 7 workloads under 3 different local memory ratios. The smaller local memory ratio means more data is on remote memory server and hence bigger slowdown. We compare Mako with Shenandoah GC and Samru. Shenandoah is a modern concurrent collector in OpenJDK, and Samru is a G1-based generational garbage collector designed for disaggregated memory. We compare them from 2 aspects, throughput and pause times. For throughput, Mako achieves about 3 times speed up compared with the Shenandoah GC. And from the figure, we can see that the smaller the local memory, the higher the throughput improvement Mako can provide. Compared with Samru, Mako's throughput is slightly worse, but in the next slide of pause time, you will see Mako has way smaller pauses. Okay, in terms of pause times, Mako achieves about 12 milliseconds at the 90th percentile pause time, which is comparable with Shenandoah, and Samru's pauses can be 2 to 3 orders of magnitude longer. On the right side is the pause time cumulative distribution for Spark PageRank. We can see that Mako's pause times are more stable than Shenandoah. So for this talk, I mainly want to convey 2 points. First, on the new hardware and system settings, it might be a good idea to bring back some old concepts and techniques. An example here is our heap indirection table inspired by object table. Second, offloading GC to memory servers makes compute near data and reduces resource contention, which improves applications throughput. Our code is open source on GitHub. Welcome to use it. And thank you for listening. Any questions?
Hey, so you talked about some of the correctness challenges with building a GC for disaggregated memory.
Yes.
So I need to talk a little bit about the performance kind of engineering of why the performance is better than Semaru. Like kind of what are the performance difficulties in building a GC like this?
You mean why our performance is better
better than this other disaggregated collector?
Like better than Semaru or?
Yeah, why is it better than Semaru? Like,
so
what does it do differently?
Yeah, for the performance of GC for disaggregated memory, we compare it with two aspects, throughput and pause time. For throughput, we are basically the same. For this work, we do not improve the throughput-wise, though we are still a lot better than traditional concurrent collectors. But for pause times, our work is way better than the previous work, the Semaru, because our pause time is comparable with the standard, while the Semaru's pause times could be like 1 to 10 seconds actually in practice.
Yeah, I'm asking what did you do differently to get those pause time improvements over Semaru?
Yeah, for Semaru, it evacuates objects during the stopped word phases. So for if they do the evacuation in the stopped word phases, then that could be very long. Because for evacuation, you also need to access the data on the remote memory servers. And this can increase the pause times a lot. But for our work, we move the evacuation to memory servers, and we do the evacuation on memory server concurrently with the application threads. So during the stopped word phases, the applications it is only some synchronization work, so it does not cost a lot of time. It's only some milliseconds.
Thank you. Let's have another round of applause. Thank you.
Thank you.